Welcome back to Valiant PE. Today's topic, computational methods and their limitations, specifically FEA. Let's go. All right, first thing we need to know, what does FEA stand for? Finite Element Analysis. And I really doubt that we're going to have any type of quantitative problem regarding FEA on this exam. I don't think we're going to be solving any equations to get a numerical value. I think it's highly likely that we're going to have qualitative problems. So that means we need to know our theory really well. Because when you have a theory-based topic, they can ask anything they want, and we're going to have to know what to do. So what we're going to cover today is two big things. Number one is how FEA works, its ins and outs, kind of how the system works. Second is we're going to understand and mitigate its limitations and shortcomings. We're going to figure out what do we need to know about how to reduce our chances of getting bad accuracy, bad results. If we know these two things, we're going to handle any question that they're going to throw at us. So, what is FEA all about? Well, simplistically, we're going to take a structure, we're going to apply a load and a boundary condition to it, and we're going to see how it reacts. That's really all we're doing. There's a bunch of different ways you can do this, a lot of different inputs and boundary conditions that you can assign, but that's really what FEA is all about. We're looking for how does the structure react. Now, because we're going to be studying for a machine design exam, we don't particularly care about the billions of types of FEA there are out there. We're going to focus on structural. Now, FEA is a very deep field, and there are people who get their PhDs in it, and we're not going to go anywhere near that deep. We're going to stay 30,000 feet and think about how does an FEA topic apply to a machine design exam. So when I say structural, I mean we've got a machine component. We're probably going to apply a force, and we're looking for how far it displaces or how close it comes to yield stress. So a sub-bullet under structural FEA is a deflection and stress FEA, and this is going to be our focus. Now, there are various other types of structurals. You've got buckling, that's key. Different than a very simple deflection and stress FEA, but still part of a structural. And you could do some vibrational stuff too. And we're not going to get into that. Just know that you can analyze frequencies and such with the FEA tool. There are also thermal FEAs, which we're not going to cover, but just know you can apply some type of heat load to a machine component and see how the heat flows through the structure. I don't think we really need to focus on this for this exam, but you need to know that it exists. So let's think about now, how does this FEA process work for deflection and stress type analysis? Well, FEA is a numerical method, and that means that we're applying some type of mathematical approximations to solve a discrete problem. Now, they're very good approximations built on loads of good math, which we're not going to cover. But by nature, you're approximating. And we take these approximations and we iterate them over and over. Iterations, or iterative, until we approach a value that we feel comfortable with that gives us our accuracy. And because it's an approximation, it has inherent errors. We're going to cover a little bit of that. But you need to know that it's a numerical method. It's not perfect, but it's very good, and it solves equations over and over again. So let's look at a very simple FEA. How might it work? How might it look in practice? Okay, you can see I've got a structure here. I've got a model, and that's the very first step. How do I set up an FEA? Well, you need a model, a CAD model. You've got to have that. Okay, I've got a 1/2 inch thick by 3 inch wide by 6 inch long bar, 1 inch hole in the middle. Really simple. The second thing I'm going to do is I'm going to assign a material to it. And I'm going to say this is a 36 steel. All right. Now, why is that key? Well, with material assignment, I know things like my Poisson's ratio and my Young's modulus. And these values are going to be critical for the software to know, how is this device going to stretch? How stiff is it? How does it move? you can't have an FEA without material assignment. That's very critical. And the third thing I'm going to do in setup is I'm going to assign some boundary conditions. Just one in this example, but I'm going to take this face right here, and I'm going to say you are fixed in space, you're infinitely stiff, you cannot move. This is orienting this object in space for the software, so it knows where everything is. Good. Now the next thing is I'm going to discretize. And that is a fancy way of saying I'm going to take this structure and chop it into tiny little bits. And the bits that I'm breaking it into are called elements. And they are 3D shapes that have flat sides and straight edges. And at their corners, we have what's called a node or nodes. And each one of these elements inside this structure here are connected to their neighboring elements at nodes. So for example, this element here, it is connected to its neighbor at this node, this node, this node, and this node. And everywhere I've got converging corners of elements, all over here I've got nodes. All right, now the last thing I'm going to do before I can maybe press go on some software runs is I need to assign an input. And again, you can get all over the place here. You can have thermal inputs, vibrational inputs, but for structural input, we're going to think, all right, I'm going to apply a load. I'm going to grab this face here on the bottom side, and I'm going to say, I want a 10,000 pound force load straight down. And that's applied all along this surface, straight down. Then I can press go now, and I can let the software do its thing. It's got all the info it needs. And then we're going to get some type of imagery about how the structure reacts. And this is ultimately what we're looking for. Now, at each one of these nodes, we have a displacement value that's been solved for. We're going to cover how that happens. And those displacement values are converted into strains based on my material. And then those strains are converted into stresses. And then you end up with a stress plot. You can see blue is very low stress and red is high. That's really it. That's super simple, guys. Only 6 steps. So now that we've seen how a really simple FEA runs, let's talk a little bit more about how does it work in specific. Let's talk about this numerical method. Okay. The first step we just mentioned, but we're going to break it into tiny parts. We're going to discretize. And this is where we're going to talk a little bit about elements. Now, there are various different types of elements. There's a bunch of different types, tetrahedral, rectangular, all that kind of stuff. But what you need to know is you're taking one big structure and you're breaking it into small pieces. So there's an element here, right there. There's an element here. There's an element here, and these are 3D, so they have faces on the inside too, and they're all connected at nodes. That's the next step, connect at nodes. So each element is connected to its neighbor at a node. Now, why do we care about that? Why do we need to know, okay, great, they're all connected? Well, the software assigns a displacement equation for each element at each node. So if I have 2 elements and they connect at a node, I have 2 displacement equations, 1, 2, for the same physical point in space. The same concept holds true if I have 7 elements that meet at one node. Right here, you can see there's 1, 2, 3, 4, 5, 6, 7 elements. So I've got 7 displacement equations for one physical point in space. And the software is going to solve those displacement equations at each node. Solve for displacements at each node. Now, the software is going to do this iteratively. So the first time it solves each of those 7 equations, they're going to have 7 different values. And they may or may not be very far apart. And it's going to do this iteration over and over and over again until I reach some type of convergence factor, convergence criteria. Convergence means eventually those 7 formulas are going to be solved closer and closer and closer until they approach one value. And there's a value, a percentage cutoff you can assign. And convergence is a measure of accuracy. And so now that I've got a displacement value at each node, displacement, I'm going to convert that displacement into a strain. And we know that strain is delta L over L. And then I'm going to convert that strain into a stress. Stress being Young's modulus times strain. And then that's how I get my stress plot, and that's really what I care about. But one thing we need to know about these elements here, we're going to call this a mesh, that's what it's called. As my element count increases, my accuracy increases. That makes sense, right? The more elements I have, the more equations I solve, the more values I get, and the easier it's going to be to converge. The downside, though, is the more elements I have, my computational time is going to increase fairly dramatically. So FEA is all about balancing accuracy versus cost. Now, meshing is an approximation. That's the key. And so it has some limitations. It's really not great at approximating corners, points, or curves, specifically curves. Think about that. We've got an element that's got sides, flat edges, and we're trying to approximate a curve with flat edges. That's going to be difficult. And you can even see here, we've got some very big elements next to some really small elements. They're not equally spaced here either, so that's a good example. Sometimes meshing is not perfect at approximating a structure. We also are going to run into some difficulties anywhere we have an applied load or applied input, or anywhere we have a boundary condition or a constraint. Now, let's take a look up here. I've said that this face is fixed in space. I've said that means it's infinitely stiff. Well, that's not true. No machine component is infinitely stiff. So immediately below it, we're going to get probably some inaccurate, incorrect strains. So we need to be careful with how we interpret our results. But these are some of the shortcomings that you're going to find with mesh. Now, let's look at how this might play out in reality. We've got 3 different meshes here. The first one on the left is auto-generated, and you can see it's very coarse. I've got some huge elements. Look how big this guy is. Elements are really big in relationship to the structure itself. And I don't have many nodes, and I have very poor approximation around my curve here. But this is going to run super fast. It may not be very accurate, but it's going to run fast. So kind of the next thing to do would be, all right, well, let's just increase our number of elements. I got elements all over the place here. I've got better approximation around my curve, but still I've got some big elements next to some little ones, and that's probably not going to give us the great results. The next thing I could do would be increase the count even more. And I've got lots and lots and lots of elements around here. I've got really good approximation here around the curve. I've got uniformly sized elements inside the curve. This is going to be really good accuracy in this run, but the computational time is going to be very slow in comparison to this guy. So we're all about balancing accuracy where we need it and computational time where we need it and not where we don't. So let's maybe look at an example of what might we see on an exam and what type of problems can we anticipate. You can see I've kind of reworked this bar to add some geometric changes here. Well, the biggest tool that we have for mitigating a limitation in approximation in meshing and mitigating errors is refining the mesh. This is really our big tool. So we're going to refine the mesh. It might be tempting, though, to say, okay, fine, I'm going to get really fine mesh all over my structure. Well, that doesn't really make a lot of sense because we're going to be have a very, very slow run if we do that. So kind of the first step in refining the mesh is only refining at required locations. Now, from a machine design standpoint, most of the time we have a machine component and we are trying to stay under our yield stress. So that means looking at this guy here, I know just by looking, I'm going to get stress around the hole and I'm going to get it around in my curves and around my curves here. I'm probably not going to get max stress here. So I don't really care too much about how accurate I am right here. I care about accuracy here and here. So we only want to refine the mesh at required locations. The second thing is we need to refine mesh where we have a stress gradient or anywhere we have a stress contour. Now that makes sense because in this guy here, we're probably going to get some type of stress flow between the hole and the notches, something in there. So we want to make sure we've got enough nodes in here to kind of capture a good contour. And then obviously anywhere we have a geometric transition or a stress concentration, we need to refine the mesh. Any machine design textbook is going to tell you, yeah, this is a notch, you're going to have some type of notch factor. Well, let's put some mesh there and we can probably solve that. So this is the big tool we're going to reach for, and here are the rules for how to use it. So let's look at maybe how I could do this. Okay, I've got this same bar here, but you can see I've assigned a region to it around this hole, and I'm going to say I want really good mesh all in here, and I want good mesh around this curve. And there's some controls in the software that you can do you can apply to get that. And I want good mesh in here in this region, and I want good mesh in here. And I don't care so much. What's my stress right there? Like, it's not going to be maximal, certainly not compared to my notches here and my hole. I know that. So this is what the mesh could possibly look like. Really good approximation around my curves. Really good. And inside my curves too. Small elements, uniformly sized, uniformly spaced. But see how I don't have a bunch of mesh up here? I'm saving computational time and only throwing it to where I need it. And here's what the stress plot's going to look like. You can see I've got very smooth contours here and smooth contours here, and they connect really well. They connect really well. So this proves that the methods I just showed you are going to work. Now, this is a really simple FEA. It gets way more complicated than this. But this might be a good example of what you could see on an exam. How are you going to, where should you refine the mesh and how should you do it? That's pretty much it, guys. And now, FEA is a really big topic. And there's loads of good stuff on the internet, good articles to read about it. My suggestion is really just to read. We're probably not solving quantitative problems here, so if you just read and you know some basic theory, you're going to be able to handle anything. That's it, guys. That's all we need to know. Remember, you don't have to be a genius to pass this exam. Thanks for watching.